to be using the ideas that we've talked about finding the derivatives and kind of beginning our conversation or continue our conversation, I should say, about some applications of it. So you're going to notice that we're going to be looking at applications we talked about in the past about the position function, then velocity, then acceleration, as well as looking at an example about population growth rates, and then finally an example of a business situation in terms of the price of something, the cost, the revenue, and marginal cost and revenue. All right, so the first thing I wanted to mention is this idea about rate of change and amount of change. If you look at the slide and read this information from the beginning of the chapter, or from the lesson, I should say, you'll notice that this stuff looks very familiar, right? This is what we've been doing in the past few lessons about finding the limit as h approaches 0 of f of a plus h minus f of a over h. We practiced that a ton in lesson 3.2. So the only thing that really is going to be used here is this idea that if you kind of mix it around, use some algebra to solve for f of a plus h, now you have this kind of new looking formula where you have f of a plus h is approximately f of a plus f prime of a times h. So we'll be using that a few times in this lesson. Okay, so let's try it here, kind of in the most basic way possible. All right, we're going to approximate or estimate f of 3.2, which I'm going to write as f of 3 plus 0.2. Okay, so my h is going to be that 0.2. So using that formula, we have f of a, so I'm going to do f of 3 plus, and this is where we're going to have h times f prime of a times f prime, I should say 0.2 there, sorry, times f prime of 3. So this is going to be f of 3, which is 2, plus 0.2 times, and f prime of 3 is 5. So 2 plus 5 times 0.2, that's going to be 1. So we're approximating it as 3. So that is the approximation for f of 3.2. Okay, again, that's really the most basic way to use this idea of the amount of change. Okay, let's talk about motion along a line. Now, this is the kind of stuff that we've already talked about the s of t being the position function, the velocity being the derivative of that, and the acceleration being the derivative of the velocity function. Excuse me. So it would be like s double prime of t is the same as the acceleration of the object. The only thing that we haven't talked about yet is this idea of speed, right? And speed is just the magnitude of the velocity. So essentially, just take the absolute value of the velocity, and that will give you the speed. Okay, so let's try this one. We have a ball is dropped from a height of 64 feet. Its height above ground in feet t seconds later is given by this position function, s of t equals negative 16 t squared plus 64. They've even graphed it for us. What is the instantaneous velocity of the ball when it hits the ground? So the instantaneous velocity when it hits the ground would be focused on at 2 seconds. All right, and so again, we've done this before, but now I'm going to show you using our derivative, our derivative rules, that we want to find the instantaneous velocity. We first need to find the velocity function. So that velocity function, v of t, is the same as s prime of t. So I'm going to find the derivative, so d dx of negative 16 t squared plus 64. Again, if you want to show all your work, you can, but I think we can do this pretty quickly. Using the power rule, 2 times negative 16 is negative 32, so that's negative 32t to the first power. And then the derivative of 64, that's a constant, is just 0. So our velocity function is negative 32t. So the instantaneous velocity when it hits the ground is going to be using that function and plugging in t is being 2 seconds, all right? So negative 32 times 2 is going to be negative 64 feet per second. So that is the instantaneous velocity, or the velocity the moment it hits the ground after 2 seconds. Now the average velocity. This is going to be the change in the, I guess I should put v there, sorry about that. This is going to be change in the distance. So s of 2 minus s of 0 all over the change in time. or 2 minus 0, right? Since it takes 2 seconds to for the ball to hit the ground. So S of 2, if you plug into, you're going to get 0, all right? T squared, 2 squared is 4, 4 times negative 16 is negative 64, so that's 0 minus, and then if we plug in 0, you get 64 all over 2, which is going to be negative 32 feet per second. Okay, so you can notice that the instantaneous velocity, so the moment it hits the ground, it's going negative 64 feet per second, but the average velocity over those 2 seconds of it falling is negative 32 feet per second, so actually half of the instantaneous velocity when it's hitting the ground. Okay, let's do another one. So we have a particle that moves along the coordinate axis in the positive direction to the right, and it's given by this position function, t cubed minus 4t plus 2. We're going to find v of 1 and a of 1, and that means velocity and acceleration, and use these values to answer a and b. All right, so let's first find v of t. Remember, that's going to be s prime of t. So that's going to be 3t squared minus 4. All right, if you're using your power rules and the sum rules. And then so to find a of t, which is s double prime of t, or just v prime of t, the derivative of 3t squared minus 4 is going to be 6t. Okay, now to find what those values are at time of 1, the velocity, the instantaneous velocity at 1 second is going to be 3 times 1 squared minus 4, which is going to be negative 1. And then the instantaneous acceleration, I should say at 1, is going to be 6 times 1, which is 6. Okay? Now, the idea of is the particle moving from left to right or right to left at time t equals 1? The way you do this is you look at v of 1, and you notice that v of 1 is equal to a negative number, so negative 1. Because it's moving, or because it has a negative number, the answer here is going to be right to left. All right, so if you're looking at analyzing your velocity and it's a positive, then it would be from left to right. Okay, so that's how we decide if a particle is moving from right to left. In terms of speeding up or slowing down, all right, you'll notice that we're moving from right to left. All right, so we're moving this direction in terms of our particle, but the acceleration is positive, right? The acceleration, or a of 1, was positive 6. All right, so that means that's going in the opposite direction. So if our acceleration is working against the way the actual particle is moving, then this is going to cause our particle to slow down. So at time t equals 1, the particle is slowing down. All right, now kind of continuing on that idea, this example is going to take it a step farther. So we have another particle moving along a coordinate axis using this position function, and we're first going to find v of t. So again, v of t is s prime of t. So using our power rule and sum rule, and difference rule actually in this case, we have 3t squared minus 18t plus 24. Okay, so that is the function for the velocity. So it says at what time is the particle at rest? All right, so in this case, if we want to know where the particle is at rest, that means the particle has a velocity of 0, right? If it has no velocity, then it's at rest. So I'm going to set my velocity function equal to 0. So 3t squared minus 18t plus 24. Factor out the 3. Get t squared minus 6t plus 8. All right. We're factoring this to be t minus 4 and t minus 2. So at time 4 seconds and 2 seconds, the particle is at rest. So at 2 seconds and 4 seconds, the particle is at rest. Okay, let's keep going. On what time intervals is the particle moving from left to right or from right to left? So this is that same idea like the question before, that if we're looking at trying to figure out where our velocity is going to be positive or negative. There's a couple ways to do this. All right, I know that if we're looking at kind of our idea of we're starting at time 0, we know at time 2 and time 4, the particle is at rest. So we're really trying to figure out what's happening in between these times, okay? So you can obviously plot it if you want, right? We can go to Desmos and we can plot this velocity function here, 3t squared minus 18t plus 24. I'm going to show you that in a moment. You can also plug in numbers if you want, right? Plug in t equals 1. Right? If you plug in time of 1, you would find if it's positive or negative. Plug in time as 3, same idea, plugging it into your velocity function. All right, but I'm going to go to Desmos and plot my velocity function. All right, so my velocity function is 3t squared minus 18t plus 24. So go to Desmos. So 3x squared minus 18x plus 24. All right, so again, from 0 to 2, right, 0 to 2, you'll notice that the red curve here is positive. All right, so I'm going to make sure that I put that it's a positive here. So our velocity is positive. Then from 2 to 4, you'll notice that all of our velocity values, as you follow this curve, right, all the velocity values here are negative between 2 and 4. So all of them are negative here. And then past 4, if you look at the curve, past 4, we're back to all positive. So to answer this question, now that I know the signs between those times, I'm going to write down that the particle is moving from left to right on 0 to 2 and 4 to infinity. And the particle is moving from right to left, right? That's my negative velocity there, from 2 to 4. So in between 2, time t equals 2 and t equals 4, in between 2 and 4 seconds, the particle is going to be moving left to right, and the particle is moving, let me try again. The particle is moving right to left on the 2 to seconds to 4 seconds, and it's moving left to right between 0 and 2 seconds, and then 4 seconds all the way to infinite seconds. Okay, so let's use this information to sketch the path of the particle along a coordinate axis. So I'm going to draw my coordinate axis here. All right, so I'm going to do some markings here for the position. All right, and I'm going to pause for 1 second just to make sure I have the right stuff. Okay, so what I want to do is I want to make this axis in Sketch using -8 all the way to 24. Let's see if I can get there. By going in between, there we go, 4 in between each. So the idea is this is going to be the position, right? So I don't want you to think this is time. What I just wrote in those little tick marks is the position. And then we're going to be starting actually in terms of time being 0, right? If we plug in 0 for t, we get 4. So that means at time equals 0, we're right here, okay, at 4 units. And then we're going to be moving to the right. Remember, we're moving to the right until we get to time t equals 2. So right this moment is when we get to that idea that we're moving. Now we're going to go from right to left. So I'm going to plug in 2 into my position function. So 2 cubed minus 9 times 2 squared plus 24 times 2 plus 4. And that's going to give me where I'm going to stop and go turn back the other way. So go right to left. That's going to be 8. That's going to be minus 36 is negative 28. Negative 28 plus 48 is 20. 20 plus 4 is 24. I'll go over that more in class to show more work. But essentially it means at 24 is when I'm going to be stopping to turn back the other way. So this is t equals 2. I'll pause and make sure I get the sketch exactly right. Okay, so what I want you to do as you sketch it, see if I help you with this, is that we're actually going to kind of like almost make like an inflection point there. So this is t equals 2. So now we're going back the other way, right? and I need to make sure and figure out at what position we're going to stop to turn back around to go left to right again. And we know that's at 4 seconds based on part C. So I'm doing 4 cubed minus 9 times 4 squared plus 24 times 4 plus 4 equals, so here we go, 4 cubed 64, that's 16 times 9, that's 160 minus 16 is negative 146, so 64 minus 146, 84 plus 96, oh man, that's going to be negative 84 minus 12, did something wrong there, but I know the answer is 20. All right, I'll go through Desmos and show you how to do that another time. So we're going to stop here at 20 and turn back around. So another inflection point, if you will. All right, so this is t equals 4 right there. And then we're going back to the other way forever. Okay, so hopefully that gives you an idea of what this, the path of the particle kind of looks like. Again, I'll try to do a better job in class of showing all the work. Okay, let's keep going. Now, last two examples are about population change and then about a business example about marginal revenue. So in terms of estimated population, we're actually going to go back to use one of the pieces that we used the very first question, which was estimating the change, right? So A plus H is approximately the F of A plus the H times F prime of A. So we're going to kind of use that idea here, okay? So what we're going to do is we're going to look at this city, and it's tripling every 5 years, all right? If its current population is 10,000, what will be its approximate population 2 years from now? Okay, so what I'm going to do is I'm going to use P of t, which is the population at time t, and I'm going to say that's equal to 10. Okay, and that's going to be, one second, let me check to make sure I have that right. Okay, so I don't want this to be P of 10, t equals 10, I'm sorry. P of t is the population in terms of thousands, so in thousands. So that means I'm going to use P of 0 is going to be 10. So as we're saying at time 0, so at this moment in time, the current population is 10,000. So P of time 0 is 10,000. So we're going to estimate the rate of change by finding, so this is going to be estimating P prime at 0, so the rate of change at time 0, as doing P of, let's see, we're doing P, it's tripling every 5 years, so P of 5 minus P of 0 over 5 minus 0. So I'm plugging in tripling. That's going to be 30,000, right? 10 times 3 would be 30,000. So that's going to be 30 minus 10 over 5 minus 0, which is going to be 20 over 5, which is 4. So we're saying P prime of 0 is equal to 4. One second, let me check again. Okay, feel good about that. So now to estimate the population 2 years from now, which is going to be P of 0 plus 2, I'm going to do, the approximation is P of 0, which I know is 10, plus my P prime, again using this idea up here, of 0 times H, which is my 2. So that's going to be 10 plus, we have our P prime of 0 is 4 times 2, which is 10 plus 8. So we're saying that the our guess, the population 2 years from now is going to be 18,000. So our guess is that it's going to be 18,000 for the population. Okay? Okay, now this last example has to do with changes in cost and revenue. And I started kind of talking a little bit about this in one of our examples from last week. But the idea here is that anytime you see the word marginal, you should be thinking that this is the derivative of whatever they're saying. So like the marginal cost is the derivative of the cost function. The marginal revenue is the derivative of the revenue function. The marginal profit is the derivative of the profit function. And there's a lot of notation in here that we'll be kind of talking about as we go forward. Okay, so let's try this example. We have a number of barbecue dinners that can be sold X, so any number, is related to the price P by the equation P of X, so the price that we're going to assign to the dinners is 9 minus 0.03 times the number that we sell, where our X is between selling 0 or 300 dinners. So in this case, if we want to find the revenue, we multiply the price that we're choosing, which is the function 9 minus 0.03x, times the number of dinners that we actually sell, which is X. So they've given us the revenue function, which is that quadratic. So we're going to find the marginal revenue function to estimate the revenue obtained from selling the first dinner after 100. Okay, so the way you do this, to find the marginal revenue, so MR is equal to the revenue, and we're finding the derivative of that, so R prime of X. So again, using my power rules and sum rules, we have negative 0.06x plus 9. So that's the marginal revenue function. And to find the marginal revenue for the first dinner after 100, the way we're going to do this is we're going to find what is the value when we plug in 100 into this marginal revenue function. So R prime of 100. So negative 0.06 times 100 plus 9. So that's going to be negative 6 plus 9, which is $3. So the marginal revenue obtained from selling the 101st barbecue dinner is $3. Now, comparing this to the actual revenue obtained from selling this dinner, so it would be the actual revenue is R of 101 minus R of 100. So that's going to be, 101 squared times negative 0.03 plus 9 times 101. And then we're going to subtract, so all of that, subtracting negative 0.03 times 100 squared plus 9 times 100. So whatever that is, it's going to give us the actual revenue that we earn from selling that 101st dinner. So let's type that into Desmos so we can get our answer. So we have, let's see, it was negative, let's put in parentheses, negative 0.03 times 101 squared. Let me make sure I got that right. Okay. Plus 9 times 101 minus, let's put this all in parentheses, minus, same thing, negative, let's do this. I'm just going to do it one at a time. There we go. Okay, let's get one number. Okay, got one number. Let's do the same thing. I'm going to copy it. So duplicate the line. And now I'm going to change it to 100. And then if we subtract 602.97 minus 600, you can see that our actual revenue that we earned from selling that 101st dinner is $2.97. So the actual revenue is $2.97, which is actually pretty close, right? If you compare the marginal revenue estimate to actually what happened, the marginal revenue estimate is very close to the actual revenue that we obtained. Okay, so hopefully you saw a few of these applications for the derivatives, and hopefully you will feel confident trying some of the homework questions. Good luck.